So, welcome to video number 6. This is subject of this video is the basics of chemistry for biology. And you may be wondering why we would be studying chemistry in a biology class. And although we have touched upon that in class, we've had a small discussion about it. I just want to repeat the fact that your body is made of chemicals. Your body depends on chemicals to function, and life itself is essentially a series of highly coordinated chemical reactions that take place in the bodies or in the cells of living things. So we're going to start with sort of the big picture and take a look at the universe itself, which is about as big as you can get. The universe we can think of as being made of four basic things, or the four basic things that we can find in the universe are matter, forces, energy, and space. And all of those concepts are important to living things. So we'll start with matter itself. Matter is the stuff that things are made out of, or more loosely, it's just stuff. So depending on your source of your definition, there's no real sort of formal definition of matter. It's used in a number of different ways in different contexts. So don't get too caught up on some kind of precise definition that has to be 100% correct. But we can think of matter as the basic building blocks of stuff. So you've got your atoms and molecules, then you've got mixtures of things like air, and water is a compound that's made up of different elements put together. Rocks are also mixtures, and proteins, carbohydrates, fats, minerals. Those are the things that you and I are particularly concerned with, because those are the things that we are made out of and the things that we use and that we need in our food. So you see in the picture I've provided for you a series of a whole collection of forms of matter that some of us might find repulsive. Looks like some liver over here. A lot of people don't like it very much, and some olives and lobster, of course, just basic types of food, all made of proteins, carbohydrates, lipids, and minerals and vitamins and so on. The second thing on our list is forces. When two pieces of matter or two particles of matter are close to each other, they interact in different ways depending on how close they are and what they're made out of. We can think of a force as being a push or a retraction between two objects, or we can think of it as being a pushing or a repelling of two different objects. Some common examples that you're all familiar with is gravity. As you know, gravity is a pulling force, magnetism, which can either be a pull or a push, and then we have electrical charges, electrostatic forces. You may have seen this before in some elementary school science exhibits where someone rubs a balloon against their hair, and then that balloon suddenly starts pulling on your hair, and you could also use that to push two balloons apart, and that is because of the positive and negative charges on the balloon. Okay. Next, the next concept is a little bit more difficult to understand or to explain. It's easier to illustrate the concept through examples, but trying to come up with a dictionary definition of energy is not all that easy, and it leads to more questions than answers. But the simplest way of thinking about energy is just an ability to do work. If you have the ability to do work, then you have energy, whatever that energy is. It's important to note that there are some laws about energy that are very important for living things and for everything, and that is, one, energy cannot be created or destroyed. Energy is sort of a constant in the universe, and we can change it from one form to another, but we can't actually create it and we can't actually destroy it. For living things, energy is needed to sustain life and carry out all of our life's activities. So your muscles moving, your heart beating, chemical activities that are taking place in your cells, synthesizing complex proteins and other types of molecules, all those activities require energy. And then the big question, of course, is where do we get this energy from? And I put two pictures on here. One is the sun, and that's typically given as the source of all energy on Earth, because although we may not get our energy directly from the sun, we eat plants that use the sun directly to produce foods, or we eat animals that in turn eat plants. So if you follow the chain of logic there, eventually you get back to plants. Lightning is a form of energy that's very interesting, that we're all familiar with. And I put that on here in part because it is hypothesized that the life itself began in a part because of lightning as a form of energy that promoted chemical activity in the early oceans on Earth. That's just one of the hypotheses about how life started on Earth. It's also interesting that if you follow any, if you're familiar now that here we are around October, Halloween time, the story of Frankenstein, and if you've seen the movies or read the book, you know that lightning, electricity was a big part of how the Frankenstein's monster was able to come to life, and so that's kind of an interesting parallel with the possible or the proposed theory of how life began on Earth. The next one also is kind of hard to define without using the term itself or terms that are synonymous with the word space. But space is a very important part of our universe. Most of our universe is actually space, as you probably know. So if you go out into the universe, you find vast, vast empty spaces, and with some scattered around in those empty spaces are here and there clusters of stars that we call galaxies, and so on. But space itself is what we also on Earth find between particles of matter, and I'll show you a little more detailed picture of that in a few minutes. It is most of the volume of every substance on Earth, so if you take anything, yourself included, most of the space that you take up is not actually physical particles, but the space between those particles. And then it's very important to note that air is not the same as empty space. I frequently get that when I ask questions about what's between the particles or what's within the space between two objects. Air is the most common answer that I get for that, but air and empty space are not the same thing, as we'll see in a moment. All right. So here I have a blown-up shot of the picture I showed you a minute ago of the water molecules. Those red spheres with the white spheres attached to them look a little bit like Mickey Mouse or a teddy bear. That's a picture of what a water molecule might look like if we could actually see the individual water molecules that we find, for example, in a glass of water. But you'll also notice that between those water molecules is what, again, some kids incorrectly refer to as air, but that is not air, that is empty space. There is nothing in those spaces between the water molecules, nothing physical except for space itself. Okay, so that's important to keep in mind. So here we have a picture of these arrows pointing to the empty space between the water molecules, and these arrows are pointing to the water molecules themselves. Up until a few years ago, it was thought that it would be impossible to actually see an atom, that we would never be able to do that because of the nature of light and the quality of the wavelengths of light that we could use to try to see something. But in recent years, we have been able to actually use electron microscopes to see, in quotation marks, actual atoms. And what you're looking at here is a sort of a matrix or an array of atoms on a flat surface. And you can see that they look sort of roughly spherical or bumpy, and what you're actually looking at here is just the electron clouds that surround the nucleus of the atoms, and we'll talk more about that in a few minutes. Okay. Of everything that you're familiar with, all everyday substances and objects and materials are made of atoms, and the different flavors of atoms are what we call the elements, and it's very confusing for a lot of students, this distinction between atoms and elements, but we'll try to make that clear as we go along. So I've shown you a few pictures here. We have pure gold crystals. These are pretty rarely found and quite beautiful in their own way. And then we have some pure carbon, sort of a lump of pure carbon over here. By the way, when you write on your papers with a piece of pencil, you're actually writing with carbon, not lead. Even though it's called lead, it's actually made out of carbon, which is good for us because lead is kind of toxic, so we wouldn't want to be walking around with pencils in our pockets made of lead all day long. And then over here we have chlorine gas. Most of the elements, in fact, are solids, but there are a few that are gases or even a couple of liquids thrown throughout the periodic table of elements. All right. Examples include gold, silver, aluminum, calcium, oxygen, carbon, nitrogen, and on and on. There's about 98 of them, as I'll discuss in a minute, that occur naturally. All right. All of those elements that I've been describing are found on what's called the periodic table of elements that is used by chemists, and anyone engaged in chemical work usually has to refer to the periodic table for one reason or another. And there's a lot of information to be gathered from this table. It's organized in a very methodical sort of way that allows us to sort of predict the chemical qualities of excuse me, the different chemical qualities of different elements. So it's a very useful thing, and we won't spend too much time in biology talking about it. We might talk about the numbers as we go along and what they mean, but just on a very superficial, basic level. You'll get more about that in your chemistry classes in 11th or 12th, 10th or 11th grade. Okay. The last thing that we'll talk about today is the structure of the elements themselves, the structure of the atoms. An atom is made up of two main parts. It's a nucleus, as you can see here, and that nucleus is surrounded by one or more electrons, which form sort of a quote-unquote cloud around the nucleus. The nucleus itself has two possible parts. It has at least a proton, and it might have a proton plus some neutrons, and the relationship between those we'll talk about at another time. The number of electrons is always equal to the number of protons, at least in the elemental form of a substance. And if you take away one of the electrons, or if you add an electron, you get something that's called an ion, which is very important. Salt, for example, that we eat all the time is made up of sodium ions and chloride ions bonded together.